right, let's dive into something really cool today. We're going to decode the fundamental language of shapes and space. And our guide for this? It's not some intimidating textbook. Nope, it's something way more authentic, a student's actual geometry notebook. We get to see how these big ideas are built from the ground up, one simple concept at a time.
So let's start with a huge question. What are the building blocks of our universe? Now, your mind might go straight to physics, atoms, quarks, that kind of stuff. But if we're talking about the world of geometry, the world of shapes and structures, the answer is actually something much, much simpler.
And that's it. It's that simple. Every single thing we're about to build, every line, every square, every complex shape you can imagine, it all grows from this one tiny conceptual seed. This is ground zero. So here's our game plan. We're going to start with that single point. Then we'll see what happens when you connect points to make lines. After that, we'll explore the corners they create. That's the world of angles. Then, the really fun part, we'll use those pieces to build our very first shape, the triangle. And finally, we'll get to know its entire family. Ready? Let's jump in.
Okay, first up, the starting point. And I absolutely love this subtitle, The Atom of Geometry. It's just the perfect way to think about it. A point is the smallest possible piece, the indivisible bit that makes up everything else. So what is a point really? Well, here's the mind-bending part. It's not a thing so much as an idea. Think about dropping a pin on a digital map. The pin marks a spot, right? But the pin itself isn't the place. A true geometric point is just the location. It has no size, no length, no width, nothing. It just says right here. And check this out. This is our source material in action. Right here in these handwritten notes, it's laid out perfectly. A point has a position, but no size and length. That one simple sentence is the foundation for everything we're about to do. Okay, so we've got these tiny individual locations in space. What's the next logical thing to do? Well, you connect them. And that's how we go from a single spot to an actual path. This brings us to lines and line segments.
Now, this is a super important difference, so let's break it down. A line is a pure concept. It's a perfectly straight path that just keeps going, forever, in both directions. You can't measure it, because it never ends. But a line segment is a piece of that. It's a snippet with two clear endpoints, which means, finally, we have something with a length we can actually measure. And once again, our notebook just nails it. For line, it says it has no endpoints and can be extended in both directions. Simple. For line segment, it clearly states it has two endpoints, and its length can be measured. Just a beautiful, clean explanation. All right, so we've got points and we've got paths connecting them. So what happens when those paths cross or meet up at a point? Well, that's where things get really interesting. That brings us to section 3, the world of angles. This is how we start creating the corners we need to build real shapes. The anatomy of an angle, as you can see from this drawing, is wonderfully simple. You just have two rays, which we call arms, and they meet at a single shared point. We call that point the vertex. And that's it. Two arms, one vertex, and boom, you've got yourself a corner. Of course, not all corners are created equal. The space or the amount of turn between the arms is what defines the type of angle. There are really 4 main types that you'll see pretty much everywhere, so let's do a quick tour. Let's start with the 2 most exact ones. Over on the left, you've got the right angle. That's your perfect 90-degree corner, like the corner of a book or a square. Then on the right, you have a straight angle. And yeah, it looks like a straight line, because it basically is. It's an angle that has opened up a full 180 degrees. And here are the other 2. An acute angle is any angle that's less than 90 degrees. A great way to remember it is that it's a little sharp, acute angle. Then you have its counterpart, the obtuse angle, which is any angle that's more than 90 degrees. It's wider, more open. Okay, this is the moment. This is where it all snaps together. We have points to be the corners, we have line segments to be the sides, and we have angles to define how those corners are shaped. We officially have all the parts we need to build our very first actual closed shape. Welcome to Section 4, Building with Triangles.
And the definition is just as simple as it gets. A triangle is a closed figure formed by 3 line segments. That word closed is so important. It's the simplest polygon you can possibly make, and it's the foundation for so much of engineering and architecture.
This diagram from the notes is basically the parts list. The 3 line segments, those are the sides. The 3 points where they meet, those are the vertices. And of course, the 3 corners they form on the inside are the angles. 3 sides, 3 vertices, 3 angles. It's elegant, simple, and incredibly strong. But here's the thing. Just saying triangle is a bit like just saying dog. I mean, there are tons of different breeds, right? Triangles have a whole diverse family, and we can sort them into groups based on their specific features. So let's dive into our final section, a family of shapes, where we learn how to classify them. The first and maybe most obvious way to sort them is just to look at their sides. We can compare their lengths. Are any of them the same? Are they all different? Let's see. So here are 2 of the big ones. On the left, we have an isosceles triangle. See those little tick marks on 2 of the sides? That's the universal symbol in geometry for, hey, these 2 sides are the exact same length. On the right is a scalene triangle. No marks on that one, because all 3 of its sides are different lengths. But looking at the sides is only one way to tell the story. Another really powerful way to classify a triangle is to look inside it, at the kinds of angles it's built with. And this should look pretty familiar, because it connects right back to what we just learned. On the left, an acute angled triangle has 3 sharp, acute angles. Makes sense, right? And on the right, an obtuse angled triangle is defined by having one, and only one, big, wide, obtuse angle. So there you have it. We've mastered the basic building blocks, and we've met the entire triangle family. And as we can see right here from our source notes, the journey is really just getting started. What happens when you add one more side? You get a quadrilateral, a closed figure made of 4 line segments. And that just leaves us with this final amazing thought to chew on. We started with a point that has no dimension at all, and from that, we built the incredibly useful triangle. So if that's what's possible with just 3 lines, just imagine the worlds you can build, the structures you can design, with 4 or 5 or 100. The possibilities are quite literally endless.